Alright everyone, welcome to this walkthrough on linear regression. In this walkthrough, we're going to just load up some sample data. We'll take a quick look at it, and then we'll build a linear model based on that sample data using some linear regression techniques. And then using that model that we create, we'll make some predictions on some new data that were not previously in the data that we used to make the model, if that makes sense. So linear regression is actually sort of the simplest algorithm that's used in machine learning. So machine learning has been a big topic, especially in tech in recent years. But the general idea with machine learning is to build a model based on data that we already have, and then use that model to make predictions on data that we don't have or things that we don't know. So linear regression is really the simplest form of machine learning, if you will. So we'll keep it simple in this one. We'll just load up the salary data. So we'll go ahead and call it salary. And then we'll go ahead and make this CSV available to you wherever you've been downloading the data, but it's just called salary data.csv. If we take a look at the salary data, we see that there's two columns. The number of years of experience an individual has, and the salary for that individual. So let's go ahead and just get a scatter plot going for that, so we can take a better look. And we notice the years of experience here on the x-axis, salary on the y-axis. We notice a general trend in that the number of years of experience somebody has usually means that they're being paid more. So these individuals with about 2 years of experience are making around $40,000 a year, whereas these couple of individuals with, looks like, over 10 years of experience are making about $120,000 a year. But the general idea here is this trend, where the number of years of experience really determines what the salary is. And I want to perhaps introduce new vocabulary, or just remind you of some old vocabulary, but that is of the dependent and the independent variable. So the independent variable in this case is going to be graphed on the y-axis, or excuse me, on the independent variable is graphed on the x-axis. So the number of years of experience, it would be the independent variable in this case. And then we have the dependent variable graphed on the y-axis. So salary, we can think of, depends on the number of years of experience that individual has, which is something we would expect in the real world, right? Somebody with more experience generally makes more money than somebody with a little bit less experience. So what we would like to do is go ahead and make a linear model with some formula y equals mx plus b that sort of describes this trend that we're seeing in the data, or summarizes the trend that we're seeing in the data. Doing so in R is really easy. All we need to do is, well, let's give this model a name first. Let's just call it linear model. The function that we use to make a linear model is lm. And we're going to use a general sort of syntax for this, where we want y as a function of x. So if you remember, the tilde is read as a function of. So we can think of y as the dependent variable, so the dependent variable as a function of the independent variable. Or in our case, salary as a function of the years of experience. Now, we don't actually have anything called salary. It's actually within the data frame salary, so we need to add one more parameter, that is data equals salary. So we should be able to run that without any problem, and we have our linear model. Let's take a look at what exactly our linear model looks like. If we just print it out, we get the original call that generated the linear model to begin with, and then we get these coefficients. So the coefficients, if you remember back to like an algebra course, we thought of lines as just equations of y equals mx plus b, right? Well, these coefficients are, the one for the intercept is the b, so the y-intercept. And this one for years experience is the slope, or m. So another way to think about this is, for every year of additional experience that you have, at least in this data set, you are earning about $9,450 more than you did last year. And theoretically, somebody with zero experience would start off with a salary of about almost $26,000 per year. So that's a great way to think about this, but it might be better to see this in a more graphical sense. Thinking about equations and stuff like that sometimes isn't the best way to think about these things. So we should plot the linear model on our existing plot. If we start with plotting the salary, and then we add an AB line, the only thing that we have to input into the AB line is our actual linear model. So if we run those lines of code, we should end up with this diagonal line whose slope is $9,450 per year, if you want to think about it that way. And the intercept is this 25,700, a little bit lower than the graphed region. Now you'll notice with our linear model, anytime so say that we said somebody's been working for four years, what is the prediction that our model would give? Well, the model would just go right up to the line at the point of 4 years and return the exact value on the line as our prediction. You can see that those predictions aren't exactly the case. For example, for this individual here, he's been working for maybe 5.5 years, more or less, and his salary is actually a little bit higher than the predicted salary. The predicted salary would maybe be about $75,000 a year. It looks like he's making a little over $80,000 per year. So that difference in the actual value in the real data and the predicted value is called the residual. So let's take a look at a plot of the residuals. Or rather, let's add a little bit more detail that allows us to see the residuals a little bit better. This little bit of code isn't necessarily something that we need to know off the top of our heads, so I'll just go ahead and run through it really quick. But we'll go ahead and plot the residuals with this bit of code. So we'll get into a little bit more about how this predict is working in just a moment as well. But you can see now on our plot, we have nice red lines that show the residuals, or the distance between the predicted value, what the model would predict for that observation, and the actual observation itself. So generally speaking, the way that this model is made is by iterating through several different models that have maybe different slopes or different intercept values, and finding that model which has the lowest sum of residuals. So the sum of residuals would be the sum of all of these red lines, and the model which has the lowest sum of residuals is the best linear model for the data. We can also think of the residuals as error. So there is some error in our model. Of course, no model is perfect. That's why it's a model. And so we can use these residuals to actually calculate stuff like 95% confidence intervals, et cetera, for our actual predictions. One other thing that we can look at is the summary function. So if we wanted a summary of kind of just the statistics of our linear model, we have that here. It has a little bit more information about the residuals, such as the minimum residual and the maximum residual. And these distances here are not the actual value terms, so you can have a negative residual or a positive residual, for example. Ideally, with these residuals, you would see that, for example, the mean and the max residual are equidistant from 0. For the same goes for the first and third quartiles. You would expect that these residuals are approximately symmetrically distributed, and so you expect to find these about equidistant from 0, and you would actually expect or hope, in an ideal sense, that the median was 0, the median residual. And you can go through sort of graphing residuals, seeing if your residuals are normally distributed, etc., etc. We won't necessarily cover that right now. We then have a review of our coefficients. So these are the same coefficients that we looked at before with these values. But in our summary, we actually get a standard error for those values, along with a t-value and a p-value. One interesting thing to check, and one important thing to check, is that the p-value for the variable in question is very close to 0. That just gives you the idea that the number of years of experience is definitely a statistically significant factor in how much pay somebody's getting. If you run a linear model and you find that the p-value is not statistically significant, then maybe you should look at modeling that phenomena with a different variable. And generally speaking, a linear model with a variable that's not significantly correlated to the actual outcome is probably not a very good linear model to begin with. And then there's more about the r squared values, etc., which we won't necessarily cover very much. The r squared being close to positive 1 just tells us that there is a significant positive correlation in the data. If these r squared value is closer to 0, it would indicate that that's probably not a very highly correlated set of variables. And if it's close to negative 1, it indicates that we have a negative correlation between the two variables, but that is significant, if that makes sense. I guess this is r squared, so it actually doesn't indicate directionality, so I digress on that. But. All right, well, that's a pretty good summary of our model. But remember, sort of the big idea here is that we want to end up making real-world predictions with our model. So one of the predictions that we could ask our model to make is, let's say that we have some individual in the company who, for one reason or another, we need to predict their salary. And we know that they've worked for X number of years. We can actually take that X number of years and travel up to the line and then make a prediction on the salary based on where that is on the line. R makes it really easy for us, though. Let's say that we have a couple of predictions that we want to make. We'll call it new data. And the prediction function actually requires that this is a data frame, so we'll use the function data.frame. And we'll give it the parameters, or rather, when we build this data frame, you'll notice that I need to use, for the column header, years experience, the exact same variable that I used when I actually made the linear model. So remember, this is the independent variable name, which is graphed here, or shown on the graph here. We have to use the exact same name as we used in our linear model here. So let's just give a couple of example values. Say somebody's worked there for 1.7 years, 4.8 years, 6.4 years, and 11.1 years, just as a couple of example values. Now, I should be able to use the function, well, let's call these predictions first. Predictions. And the function is predict. Now, the object, well, there's some thunder in the background. Hopefully you can hear that. That's really cool. The object that we're going to feed it is our linear model. And the new data that we want to make predictions based off of is our new data equals a new underscore data, the data frame that we just made up on line 16. So if we run that, we should see in the console that we didn't have any issues. And we can even take a look at the predictions that we just made. And we can see that the first prediction made, which would have corresponded to 1.7 years of work, so 1.7 would be maybe around here. We predicted they make about $42,000 a year, which definitely jives with the graph. The second person, about almost 5 years of work and makes about 71,000, etc., etc. These would be our predictions based on our linear model. So, if you followed along making that linear model, I have to congratulate you on making your first machine learning model, technically. And hopefully you learned a great deal about linear regression just generally as we walked through that. I should mention that real data, this sort of simulated data set, is very clean, had a great correlation coefficient, etc., etc. Real data might be a little bit messier than this. You might not get super ideal residual values and stuff like that. But generally speaking, as long as you have a statistically significant correlation between two variables, you should... Well, there's that thunder again. You should have a pretty good model there. All right, well, thanks for watching. Hopefully that helped.